In this video, I want to focus on the act of proofwriting as an act of writing, crafting a mathematical proof. It's not just doing mathematics, pushing a lot of symbols around, following rules. It's also really an act of writing. It's writing words, it is writing arguments, it is writing with a style that is clear and engaging and personal. It's pre writing and revising. It's everything that you know and hopefully love from the writing process. So, in this video, I want to give an example of how I go about writing a mathematical proof and some of the directions this can go. So, here's the theorem that I want to study for this video. Theorem, this is about modular congruence for all integers a, b, and p. If a is congruent to b modulo p, then also a squared is congruent to b squared modulo p. So if I square my two integers, then if they started congruent modulo p, the resulting squares are also congruent modulo p. So let's kind of start with some pre-writing. So I'm going to call this pre-writing here. So this is not yet a proof. This is some pre-writing. So what do I know? And when we're pre-writing, we can be as casual as we want. What do we know? We know that if A is congruent to B mod P, that means that A minus B must be equal to K times P for some integer K. Now, what I'm going to do here, and this is a bit of an algebra trick, and so it might be a little bit tricky to see this the first time. What I'd like to do is I would like to somehow say something to the effect of a squared minus b squared is congruent to h times p for some different integer h. Now, how do I get there? Well, what I can do is, if I'm sneaky, I can remember that a minus b, a squared minus b squared, sorry, is equal to a minus b times a plus b. So this is my insight. A minus b times a plus b is equal to a squared minus b squared, and that is going to be equal to h times p for some p. How do I kind of work this out? Well, okay, if I know that a minus b is equal to k times p, that means that if I hit that on both sides with a plus b, so a plus b times a minus b is equal to a plus b times k times p. And then I simplify, okay, well, this is a squared minus b squared. And so now what I can see is that my h, the integer h I need, is a plus b times k. So this is my insight, if you will. This is not a proof. This is not a mathematical proof. It's because it's not writing. But it is a start. It helps me understand where I am going. Once I have a mathematical insight, I can kind of go in multiple directions here. So we could, if we wanted to, write a proof fully in logical symbols. All logic all the time. We can try that out. So here is the logic version of this argument. If I were to write this out as a logical deduction, here's what I would do. So let's call this a first proof. I'm putting proof in quotation marks here. What I would do first is we would start with our premises. So our premises are that a, b, and p are all integers, and furthermore, that a is congruent to b modulo p. Okay, so now what we do is we start making deductions from these premises using our logical steps. Here, my first line, L3, is going to be that P divides A minus B, and I know that from a previous theorem that we proved in these videos. Next, and I should always say what line or premise I'm using here. So that's a previous theorem with P2. Okay, next, line 4. If I know that P divides A minus B, I know by definition that means that there's a K in the set of integers such that A minus B equals P times K. So this is the definition of X divides Y with L3. Next, what I can do is I can say, okay, line 5, let's hit that on both sides with A plus B. So A plus B times A minus B equals A plus B times PK. And that's algebra with L4. Okay, moving on, line 6. Okay, so in line 6, I'm going to simplify. A squared minus B squared equals A plus B times PK. Okay, I know that because of more algebra. And I'm using it on line 5. Line 7. Okay, now this is a good place to check that A plus B times PK, or sorry, times K rather, is in the integers. And indeed it is. Integer rules. If I add, subtract, or multiply integers, I get more integers. Okay, almost home. It follows, I've checked my conditions now, it follows that P divides A squared minus B squared, and that is from the definition of X divides Y using L6 and L7. And now I'm home. L9 from a previous theorem, I know that this is the same as saying that A squared is congruent to B squared modulo P. So this is the logical deduction version of this argument. This is also valid. This is, in some sense, a correct proof. You can't really argue with this. But it's quite abstract. It can be difficult to parse all the symbols. And technically, we have a guide kind of where we're going and what follows from what, but it's not necessarily very easy to read or learn from or understand. And so, although in mathematics, we really like to know that it's possible to write these kinds of logical deductions for our theorems, it's not the way that we usually do it. But because we know that we can do it now, we're in a position to really write something that's much more clean and able to be understood. So let's finally do that now. Let's write our proof of this statement. This proof, our idea is that we are going to take this insight from the pre-writing and these logical steps from what you might even think of as our first draft, and we're going to revise that into something that is easy to read, learn from, and understand. So here we go. Proof. Let A, B, and P be integers. Let's start with that. And suppose that A is congruent to B modulo P. So what we've done is we've stated our premises. We've just done it in English language, but you can see, okay, premise 1, A, B, and P are integers. Premise 2, A is congruent to B mod P. Now we'll keep going. Then, by a previous theorem, P divides A minus B. So what's going on here now is I'm going more or less line by line. I'm saying, okay, I can follow this argument now because I kind of seen the big insight. I've seen it in logic. I'm going to kind of write out the words that would correspond to this logical argument in an engaging and readable way. So I'm going to keep going. I'll actually even sort of turn this period into a comma. I'm going to keep going in this sentence, which means that there is an integer. We'll call it k, such that a minus b equals k times p. So this is our definition, and we're now essentially stating line 4 here. Next, and because this is a tricky step where there's some algebra going on, it's helpful to tell your reader that you're about to do something specific. So what I'm going to say here is next, let's multiply both sides of this equation by a plus b. So I'm not in a rush. I'm taking my time to telegraph to my reader what I'm doing. When we do this and simplify, we get, so now I'm telling the reader I'm going to do some math now. I'm going to do some multiplication and I'm going to simplify. A plus b times a minus b equals a plus b times k times p, or a squared minus b squared equals a plus b times k times p. Notice here I'm putting a period because every time I'm writing a proof, I end with a sentence. I'm writing a sentence, and so I end with a period to signify that my sentence is complete. And I put a period there even if what I've been doing is math. I still have a period, so I'm still completing a sentence. Okay, so now I'm almost done. Since a, b, and k are all integers, this implies that p divides a squared minus b squared. So here I've decided, okay, there's some things that I don't have to justify every single time. So here I said, oh, a, b, and k are all integers. What's unsaid here is that means that a plus b times k is also an integer. I've taken the contextual step that, hey, I can let that slide this time. I don't have to say it explicitly. My reader is familiar with that idea. Okay, I've shown that p divides a squared minus b squared by a previous theorem, the same previous theorem that we mentioned earlier. This means that a squared is congruent to b squared modulo p, as was to be shown. And we can put our satisfying end of proof square there. So, summing up, I started with a theorem that I wanted to prove. And the first thing I did was I kind of got a sense for how this was going to work. And I called that pre-writing. I said, okay, if I kind of see the fundamental algebra or math step in here about how this is going to work, that's my first step. I need to see that first. Then, and you don't always do this, in fact, you very rarely do this, but you can really lay it out logical step by logical step in symbols in the form of a logical deduction in standard form with your assertions and your justifications. We don't usually do this, but it's good to know that you can, because if you can, then you can write clear English that will offer your reader engaging, compelling proofs that they can learn from. So here's my example of a reasonable proof that really takes the structure of this logical deduction and just tries to sort of strip away some of the symbols and put it in readable words that we can all sort of understand with and digest relatively simply. But it has the backup of this rigorous logical structure that we're looking for. So when you're thinking about a proof, you want to think about something that looks like nice words. Proofs are usually paragraphs, so they look more like prose than they look like mathematical formulas. But behind that paragraph and communicated through that paragraph is a rigorous logical structure where everything is technically airtight. So proofs are really writing. And when you're writing your own proofs, I want you to think about, okay, I'm going to do some pre-writing. First, I'm going to see the fundamental idea here. And then I'm going to revise my way into my final proof that I share with my readers.